Hello, I'm Mike Platt, Technical Services Engineer for Corrocoat Limited. This is one of a series of technical videos we are producing to inform our customers and colleagues about the various technical aspects of protective coatings. This particular video is on the subject of cathodic disbondment testing. Cathodic disbondment testing is one of the tests used for assessing the performance of a protective coating. It's where a coating disbonds due to a cathode reaction at a damaged site through the coating to the substrate. This disbonding occurs by generation of hydroxyl ions, which raises pH at the coating substrate interface and causes the coating to disbond. This is important in many applications because the ability of a coating to resist cathodic disbondment correlates with performance in other areas, such as adhesion and moisture vapor transmission. Disbondment of coatings often occurs on items protected by impressed current systems, such as pipelines, marine structures and ocean-going vessels, but can also occur on other plant and installations where cathode reactions are taking place due to the corrosion process. It is therefore important to understand the coating's ability to resist cathodic disbondment in order to assess its performance for various applications. Several tests for cathodic disbondment have been promulgated over the years, but the one we prefer at Corrocoat is the most aggressive, can be carried out quickly and gives accurate, repeatable and consistent results. It's a sort of sorting men from the boys test. The downside is that the area of disbondment is sometimes difficult to ascertain. The cathodic disbondment test is generally carried out in accordance with British Standard 3900. The test is carried out on mild steel test panels, 3 mm thick, prepared by abrasive grip blasting to a cleanliness standard of SA 2.5 in accordance with British Standard ISO 8501-1 and vacuumed to remove all grip blast residues and dust. The plate is prepared to the specification and the coating applied to the manufacturer's recommendations. Coating thickness is measured with an electronic dry film thickness gauge and checked for coating integrity with a spark test holiday detector. This ensures that the panel is free from defects and complies with the specification. A hole is drilled through the coating to create a damaged site using a 6 mm drill in the centre of the test panel, ensuring that the coating is cleared through to the metal substrate over the whole drilled area. The plastic tube is placed on the coated panel centrally over the damaged site and sealed to the coating surface using the silicone rubber sealant to form a cup. The platinum anode, 0.8 mm diameter, is placed inside the cup and fastened to the plastic tube so that the distance between the anode tip and the damaged site is approximately 10 mm. The test panel and anode are attached to the cell controller terminals. The cell controller is capable of maintaining the electrode potential of the test substrate at the specified voltage. An electrolyte solution is prepared by dissolving 30 grams per litre of sodium chloride in water. The electrolyte solution is used to fill the cup to a depth of approximately 50 mm. A voltmeter is used, capable of measuring in the range 0 to 3 volts to the nearest millivolt, and a saturated calomel type reference electrode of 12 mm diameter with a porous plug. The power unit is switched on. The voltmeter is connected between the test plate and calomel reference electrode, and the reference electrode is placed within 10 mm of the defect site. The electrical input is adjusted by means of the variable resistance in the cell controller until the voltmeter reads 1500 millivolts or other specified test voltage with respect to the calomel electrode. The voltage and current are checked, recorded and adjusted if necessary every day for the first 4 days and then every 4 days thereafter. In addition, the electrolyte solution is topped up by the addition of distilled water every 4 days. The electrical voltage and amperage records are examined. Notes are taken when any deviation occurs. A large increase in current consumption usually indicates the breakdown point. A slow increase indicates a gradual loss of adhesion from the defect site. A report is made on the changing colour of the coating, the current deviation and the extent of disbonding as an average distance from the damaged site. A record of the panel is made by either photograph or photocopy. The test is continued for 28 days or longer where previous test results have shown little indication at this period, given good test results. The electrical connections are removed and the electrolyte poured out. The coating is then inspected. The plastic tube is detached and the panel rinsed in fresh water before being dried with a lint-free cloth. Radial incisions are then made into the coating through to the substrate using a sharp knife, or in the case of a rigid hard coating, a hacksaw. The incisions are made from the damaged site out across to the edge of the cup area, approximately 30 degrees apart. A chisel is then inserted under the coating at the damaged site and used to gently prise upwards. The coating is broken away until a firmly adhered edge is encountered. In this comparison, the coating on the epoxy coated panel can be easily removed with the chisel. The coating on the panel with the Corrocoat glass flake coating is difficult to remove. As loss of adhesion is not always obvious, the substrate is carefully examined to determine if there are signs of residual coating which would indicate that disbonding has not occurred. Corrocoat flake glass reinforced coating systems have excellent results under cathodic disbondment conditions. Extended tests can be carried out over 3 or 6 month periods. There are some issues in assessing the end results. Whether the coating is a thick or thin film, elastomeric, rigid or brittle, the exact area of disbondment can be difficult to measure. To assess the area of disbondment, it is preferable to use a marker. The one we use at Corrocoat is phenolphthalein. Once the surface has been cut by suitable means, a drop of phenolphthalein is placed in the centre of the area, turning pink and indicating the spread of corrosive ions. In this comparison, the coating on the epoxy coated panel, the colour spreads rapidly, turning pink the area of concentrated hydroxyl groups to show the extent of spread of OH corrosive ions. The Corrocoat glass flake coating, cut with a hacksaw, has a high resistance to moisture vapour transmission, high electrical resistivity and high adhesion value, and as a consequence, excellent resistance to cathodic disbondment. This type of coating is a rigid material and is often difficult to determine where the disbondment is due to mechanical chipping and where the disbondment has occurred solely due to the cathode effect. Erroneous results have been obtained in the past due to the incorrect assessment of the extent of cathodic disbondment. This is a chart showing that cathodic disbondment and moisture vapour transmission are clearly related. When evaluating coatings, it is important to look at performance rather than formulation, such as it must have 25% glass flake in the dried film, or it must be an epoxy. This limits the substitution of a coating which will perform better in that particular environment. All testing of coatings should be performance-based. This test is just one means of measuring the effectiveness of a coating, not just cathodic disbondment, but coating performance. Thank you for your interest and watching this video.